So, in earlier class I have discussed about the X-ray production and its properties. Then I have discussed the diffraction of light and diffraction of X-rays. Now, you have seen that this basically from diffraction of X-rays, so their natural grating we use the crystal of some materials. So, so that diffraction is that 2D sin theta equal to lambda, that is the Bragg condition for getting the interference maxima that we tell the Bragg peaks. So, henceforth I will call it Bragg peaks. So, from X-ray diffraction we get Bragg peaks at different angle theta that we tell Bragg angle, and that each Bragg peak, since we are considering only first order n equal to 1. So, each Bragg peak corresponds to the to a particular set of parallel planes which is having a particular d. So, different Bragg peaks will get. So, the different Bragg peaks are from different set of parallel planes. Okay. So, they have different d. So, analyzing, so from X-ray diffraction basically we measure d, experimentally we measure d, not d, experimentally we measure Bragg angle theta, okay, Bragg angle theta. So, theta for different Bragg peaks, if you know theta for different Bragg peaks, then since lambda is known to you, so 2D sin theta equal to lambda, lambda is known, theta we are measuring from the experiment, then we can calculate d. So, d is the planar separation. So, there are few Bragg peaks in one experiment. So, we will get different d value, different d value. Okay. Now, d is the planar spacing. So, d is related with the lattice parameters a, b, c and their angles alpha, beta, gamma. Okay. And from that relation, so solving you see solving these 2-3 equations which will come from for 2-3 Bragg peaks. Okay. 2-3 Bragg peaks we will get d1, d2, d3. Now, d1 is related with the Miller indices and the lattice parameter. Okay. So, if you solve them, then you will get this lattice, you can find out the lattice parameters. A, what is the a value, what is the b value, what is the c value, what is their angle. So, that means if you know them, then you can tell what is the structure of the crystal. So, so that is what I want to discuss now. One should know, one should have clear idea about the crystal structure, then only you will be able to analyze the X-ray diffraction data and extract the information. So, all materials in universe, whatever the materials you see, so they are in different form, phase or form. Okay. You can see this gaseous form, liquid form, solid form, plasma form, okay, and some other forms are there, but in nature generally these 4 forms we see. Other forms in laboratory one can generate. Okay. So, now this let us concentrate in the solid state part, solid state form. So, solid state material. So, all materials are made of atoms. So, generally made of 92 types of atoms. Now, later on there are more atoms are discovered in the laboratory. So, for the time being, let us just consider this 92 types of atoms. Okay, all materials, they are made from these 92 types of atoms. Okay. Now, this question is, so atoms, these materials is made of atoms. Okay. So, this how these atoms are arranged in the material. So, whether they are arranged in regular way or throughout the material, they are ordered in throughout the material, or they are ordered in just region wise, or they are randomly oriented, there is no order. So, that way we classify the material this amorphous, single crystalline and polycrystalline. Okay. Amorphous, where these atoms are randomly oriented in the material. So, then we tell this the amorphous, that single crystalline, if atoms are completely arranged in the material, throughout the material this arrangement are perfect, then we tell single crystalline. Now, in between these two, then there is a partially arranged. Okay. So, then we tell is the polycrystalline. So, region wise, in some region, so I have a picture, to tell it. So, here you can see the atomic arrangement. So, if atoms are perfectly arranged like this, so then we tell, you see clearly you can see they are arranged, they are ordered. Okay. So, it is a single crystalline. If region wise, in this region this is ordered, in this region this is ordered. So, these we tell the grain. So, these grain are ordered, but there is a difference in direction of this ordering direction from this region to this other region. So, this we tell this is another grain. So, grain itself is, these atoms in these grains are ordered, but grain to grain there is a boundary, because this boundary comes because of their slightly different orientation. Okay. So, this type of material is called, is not throughout the material, it is not following a same ordering. So, region wise they are ordered, and as if they are randomly oriented, these grains are randomly oriented in the material. So, then we tell the polycrystalline. Okay. And if it is randomly disordered, okay, you cannot find any ordering of this atoms in this material, then we tell amorphous. Now, in case of X-ray diffraction, already I mentioned that there are planes where the electron density are maximum. Okay. Means the atoms are arranged on this plane. Now, then the same arrangement is found in another plane. Okay. It is parallel to it, same arrangement, same intensity. Okay. Now, electron density variation is there in between this, as if this electron density is very low and these are electron density high. So, high electron density, then low electron density, then high, low. So, set of parallel planes. So, this is only possible if atoms are ordered in the material. Otherwise, this type of distribution of the electron density you will not find out, and you will not expect diffraction. You will not expect the diffraction. Okay. So X-ray diffraction, if you get like this very sharp peak, okay, for a one peak, if you get one peak, okay, for a particular orientation, one peak if you get, and this is the very sharp peak, then we can tell this is the single crystalline. Okay. So, if you get this multi-peaks, we get multi-peaks, okay, from this sample. Then we tell this the polycrystalline, and if we get this broad peaks, then we tell this the amorphous material. So, seeing the pattern of the diffraction, seeing the diffraction pattern from the materials, one can tell whether the material is single crystalline or polycrystalline or amorphous. Okay. So, that means this using X-ray diffraction we can identify material, what is the crystal structure of the material. So, if it is amorphous, there is no question of crystal structure, because there is no orderedness of atoms in the material. Okay. So, now this X-ray diffraction only it can study the crystalline material. So, that is why I wrote X-ray diffraction and crystal. Okay. It is not to study amorphous material. So, crystal structure, crystal. So, now crystal structure, as I told, these two material have two types of structures. One is single crystalline structure and another polycrystalline structure. Okay. So, seeing the diffraction pattern, one can immediately tell whether it is single crystalline material or it is polycrystalline material. So, hopefully you know, but still again I am revising, I am telling in my own way, just keeping aim to correlate with the X-ray diffraction. So, here I have drawn a lattice. This is called a point lattice. It is the point lattice. You see, in space I arrange atoms, and this, from that arrangement you can see there are, it's a one can divide these whole materials into some units, into some units. Now, one can tell that it's this lattice, one can get repeating this unit in space. Okay. So, one unit I have taken from here and drawn here. So, this is called unit cell. So, this is nothing but the repetition of this unit cells in all three directions, it will give the lattice. So, if you know about the one unit cell, that means you will know about the whole crystal, that crystal material. Okay. So, when we tell that we want to know about the crystal structure, that means we want to know the unit cell of a crystal. In unit cell, how we define unit cell? We define, you see, it's a 3 axis, A axis, B axis, C axis, and angle between them is alpha, beta, gamma. You see, alpha, beta, just A, opposite of that A, this angle is alpha, opposite to B, angle is beta, opposite to C, angle is gamma. Okay. So, these are called the lattice parameter. These are called the lattice parameters, and these lattice parameters is A, B, C, alpha, beta, and gamma. Okay. So, if I know these lattice parameters, and these lattice parameters are related with the D equal to, so there is a relation for different structures. So, if you know D, you can find out these lattice parameters. If you know lattice parameter, you can find out D. Now, in between you need another things. So, lattice parameter and D, okay, this in that relation there is another parameters we need, that is called Miller indices. So, what is Miller indices? HKL, that also I will tell you. Now, one important thing, I am talking about the lattice and lattice point. Lattice is made of lattice points, and these lattice points are orderly placed in a space. Okay. Now, what is crystal structure? Lattice is not the crystal. The real crystal is lattice plus basis. So, lattice, the structure is a mathematical concept. Okay. If I tell you the A, B, C value and alpha, beta, gamma value, just you can produce lattice points in space. Now, real crystal is basically this one atom or a group of atoms attached to each and every lattice point. Okay. So, that is basically total this lattice and basis together is called the crystal structure. So, this is very important. So, as if these lattice points are reference points and we have to put real atom, one atom or a group of atoms to the each lattice point in same way we have to attach. Okay. Then we will get the real structure of crystal. So, that is why I have written lattice plus basis equal to crystal structure. So, now this crystal structure, this fortunately this thousands and thousands materials, and they have different types of different type of structure. Okay. But fortunately this all structure it can be so all materials whatever the structures are there, it is similar to this whatever the material, but they are made of 1 or 2 or 3 or some n number of atoms. Okay. But that atoms is from this 92. Similarly, this all materials whatever the structure is there. So, that structure in terms of unit cell, so only 14 types of unit cells are from symmetry, only 14 types of unit cell exist. Okay. So, now can you imagine that 14 lattices are there, is called Bravais lattice. So, real crystal of a material, so its structure, its unit cell or its lattice, it will be one of these 14. Okay. So, these 14 Bravais lattice is basically they have different type of lattice parameters. Okay. So, that is why here this cubic, orthorhombic, tetragonal, rhombohedral, hexagonal, monoclinic, triclinic. So, these are the system, and in those system this how these lattice parameters are different, how the lattice parameters are different. So, here this we tell cubic, this cubic system when A, B, C are equal and their angles alpha, beta, gamma 90 degree. Okay. It has 3 types Bravais lattice. So, it is a simple body centered, face centered, and the symbol is a use PIF. Okay. So, similarly tetragonal A equal to B is not equal to C. So, this way you know, but still I have mentioned here. So, when you are studying your crystal, your sample, what is the structure of this sample? So, basically from X-ray diffraction I can get different Buckfick, means I can get different d value. Now that d value is basically equal to some relation of this ABC, this angle and the HKL Miller indices. Okay. So, let me just tell about the Miller indices. You know, but still let me tell you what is the Miller indices. Miller indices is how we have defined Miller indices. Okay. So, this is the now in crystal these lattice points are arranged. Now there you can choose a plane, and now how we give name of these planes. So, we see that planes or other planes parallel to this. So, where they have cut this A axis, B axis and C axis. Okay. Here I have shown one plane here. If it is A axis, it is B axis, it is C axis. So, here you can see this plane, it cuts you see C axis, it cuts C axis and it cuts A axis, and it is parallel to the B, So, where it will cut? It will cut at infinity. Okay. So, unit here, 1 unit of, so you can tell that this it cut at this lattice constant along this A axis. This is its a unit length is A. So, it may cut NA. So, at A or 2A or 3A, so NA, okay. Then it can cut B at infinity and C at NC, okay. N is either 1, 2, 3 like this, okay, but in units of C, okay. So, what is the A distance? A distance is you see this distance between these two lattice point along on this A axis. Okay. So, what is the distance between two lattice point, minimum distance two lattice point on the A axis. So, that is the A, similarly B and C, okay, and their angle of course it is there. So, we take whatever the factors with A, B, C, we take inverse of those factors. If it is n, so 1 by n, ratio 1 by infinity, ratio 1 by n. Okay. So, in this case both cases is same. So, that is why I have taken n, otherwise one has to take defined value. So, if you take from there, so here you can simplify and you can get 1:0:1, 1 ratio 0 ratio 1. Okay. So, this plane, then we tell this 101 plane, 101 plane. 101 plane means it is not one plane, it is a set of parallel planes. It is a set of parallel planes like this. Okay. So, similarly you have 100 plane, you have 110 plane, you have 111. So, many planes are possible. Okay. And one can find out from A, you know A, B, C value. What is the planar distance, what is the normal distance between these two planes. So, that is the planar distance d, and this d have relation with A, B, C, alpha, beta, gamma. So, for different structure, for cubic, for tetragonal, for orthonormic, so different structure relations are one has to, it is given in book, you have to find out, you have to just read it, or one has to derive. So, I have not shown here these the standard things how planar spacing d is related with the lattice parameters A, B, C, alpha, beta, gamma. So, that is there. So, when X-ray is diffracted, okay, from from a crystal grating, from a crystal plane. So, these sets of parallel planes, you see X-ray, if it falls like this, so it will see this space between these two planes is basically it is like a slit width. Okay, it is like a slit width. So, it is but this width is 2, 3, 4, maximum 5 angstrom. Okay. So, which is comparable to X-ray wavelength. So, that is why this is a very God gift natural grating for X-ray, and it is a so tremendous powerful technique diffraction. Each and every one who do research, they use this X-ray diffraction and to know their structure of the sample, not only structure of the sample, some other important information also one can find out. Okay. So, this is the mirror into HKL. Okay. So, planar spacing we write DHKL. Okay. So, DHKL. So, DHKL, why we write? Because in one crystal there are many numbers, many numbers of planes, and basically we get different Bragg peaks, and we measure the angle of the Bragg peak and we calculate D, and D is related with H, K, L, A, B, C, alpha, beta, gamma. So, if 7 unknown is there, so you need at least 7 Bragg peak to set 7 equation. So, you can solve it, then you can know all parameters. Okay. So, depending on that number of, in cubic case it is a simple only one parameter, A equal to B equal to C, only A you have to know, and HKL of course. So, fortunately this there is a data X-ray diffraction data for all sorts of structure, that is called JC, I think some internationally acceptable some database are there. So, there for all sorts of data these Bragg diffraction patterns are given. Okay. Their intensity, their Bragg angle position, Bragg peak position, all are given for all sorts of structure. So, generally what we do, we just do the experiment, get our diffraction pattern from our sample, and that diffraction pattern we compare with the database. Comparing with the database directly, that database itself will tell us what is the crystal structure of the sample. Okay. So, but that database is basically it is made from that calculation. Okay. The things I told you. So, it is just to save time we use that database and get the information. If I have the experimental XRD pattern of my sample, comparing with the database, I will be able to find out the crystal structure. But there are some other things which you cannot find out from this database. So, is it just application of this X-ray diffraction? Is it only for determining these lattice parameters or something else? So, there are something else. What else you can find out from the X-ray diffraction experiment? So, here so Bragg, we have to, so here I have shown the typical XRD patterns from a sample, okay, from a sample. So, this either from single crystalline sample you can get also this kind of pattern. In that case you have to vary the angle of the sample with respect to the X-ray direction, okay, and then you are varying and satisfying the Bragg condition for different planes. So, that time I told this for polycrystalline and this for, so this looks like polycrystalline, but it may not be. So, without varying the angle, of the sample with respect to the X-ray, if we keep this, this sample fixed, X-ray also fixed, then just the detector, if we move at different angles, and if you find different Bragg peaks like this, then it is polycrystalline. Okay? Then it is polycrystalline. And if it is single crystalline, then what will happen? If it is single crystalline, then if you just rotate this one, this your detector, then you may or you may not find any peaks, okay, because this all planes are fixed with respect to the surface of the sample. So, here to study the single crystalline, we need option to vary the angle. So, if you just vary the angle, so then you will get one peak. If you vary more, then only you will get another peak. Okay. So, if you just vary at fixed at a one pace, and if you are moving this your detector, so you will see only one peak, then it is single crystalline. And without varying the sample or just you have varied and fixed it, now you are rotating your detector, okay, with all sorts of angle. So, then if you see the many peaks at different angles of the detector, so then it is the polycrystalline. Anyway, so here the peak here, this we tell this Bragg peak. Now, this Bragg peak for a particular sample, these peaks have come different planes, but their intensity are different, their intensity are different. So, this intensity of Bragg peak carries the information. So, not only the angle of the Bragg peak carries the information, intensity of the Bragg peak also carries the information. So, Bragg law, as I told, 2 DH scale. Now, I have written DH scale. So, this H scale plane. So, HKL it can be 100 or 110 or whatever. So, sin theta equal to lambda, as I told, we will take only first order. So, what is theta and what is DH scale, that I have shown here. Now, you have done experiment following this geometry and you got this kind of XRD patterns. Okay. So, if lambda is fixed, K alpha, DH scale is related to theta, right. So, at different theta you will get different Bragg peak, which specify different planes of the crystals, as I discussed. Now, intensity of this Bragg peak, so for different planes is the different. So, intensity will depend on HKL. So, it is proportional to the FHKL square. Okay. What is FHKL? This is the structure factor. It is called structure factor. FHKL is the structure factor. It depends, the structure factor depends on the distribution of atoms in the crystal plane or in its cell. Okay. So, this the atoms, how atoms are arranged on the plane. So, depending on that is the, so it will depend on the position of the atoms on a plane. Okay. So, positional information is basically we get from this, we express in terms of F H scale. Okay. So, this is called structure factor. It will tell about the structure of this of the structure or distribution of the atoms on a particular set of planes. Okay. So, that is why for different sets of planes their distribution of atoms are different. So, that is why their intensity will be different. So, from intensity one can actually find out the distribution of atoms on the planes, means or distribution the atoms in the plane. So, if any displacement, crystal may not be strongly perfect. Okay. So, if any distortion of the crystal, means the arrangement of the distribution of atoms, the way we expect for a particular structure, it may not be, it slightly changes. So, that change will come in the intensity, So, in case of single crystalline crystal, where it is very it's nicely ordered. So, as I mentioned that this peak become very sharp. Okay. So, this intensity here, it become very sharp, and in case of if it is ordered or not perfectly arranged. So, this peaks become broad, Okay. So, some disorderness is there. So, these are the, so basically there are this this angle of the Bragg peak, intensity of the Bragg peak, broadening of the Bragg peak, all these are important to study the crystal structure. Okay. So, I think yes, one more things I can tell you, that from what are the things we want to get, I kept somewhere, let me see this application. So, applying the X-ray diffraction, I have a one slide. Here I got it. So, basically this, now at least we know what is the X-ray diffraction, what is the crystal structure. Okay. So, application of X-ray, there are people use for different many to study the samples for different structural aspect. So, but main aspect we study using the X-ray diffraction, that is basically that phase composition of a sample. This is the very simple. If you have take a mixture of two materials, say aluminum and copper. Okay. So, dust of copper and dust of aluminum and then mixed it. Now, if I mixed it and give you that what is the ratio of these two what are the elements are there, what are the materials are there in this mixture you have to tell, and what is the ratio of these two or three phase in this mixture. Okay. So, these are called basically phase composition of a sample. So, determination of the relative amounts of phases in a mixture by referencing the relative peak intensity. Okay. So, first if you take this XRD pattern, so this kind of pattern, one I have shown the red and another black. So, one for say aluminum and another set of Bragg peaks, red one and black one. So, this one is for copper and another is for aluminum. Okay. Now, you just raise these two peaks. Okay. Two peaks you have to consider, one peak from this from black one and another peak from the red one. Okay. So, you choose the same plane, this which plane are common in these two, say 2 to 0 or whatever the plane. So, for a particular plane, for a particular HKL, since their d are different, so they will come at different angle, Bragg angle. So, one has to identify this using the database, one has to identify that this Bragg peaks for which structures. So, then you can know this structure of the material, and then for structure of that material you can identify the metal also, it is the aluminum and it is the copper. Now, the relative intensity of these two peaks, okay, you can find out the amount of the material because the amount of material is higher. So, scattering of X-ray, okay, or diffracted rays from that material will be higher. Okay. So, the diffracted rays from these from the materials which amount is higher. So, the intensity of diffracted rays will be higher. So, Bragg peaks whatever you will get, so that intensity will be higher compared to the for same kind of plane of the other one. Okay. So, from the relative ratio of this intensity of the peaks referencing the, here that is why written referencing the relative peak intensity, we can find out the phase composition of a sample. Okay. And of course, these are unit cell lattice parameters, as I told, only on this I told that indexing the peak, okay, means 1 1 0 peak, 0 0 3 peak, etc., etc. So, indexing peak positions, and from there theta you will get and calculate DHKL, DKHKL is related with this. Okay. So, one can find out the lattice parameter. Also, one can study the strain in the sample, one can study of the in polycrystalline sample, what is the grain size of the sample, one can find out. Okay. So, this is one formula I have shown here. This is the B as a function of theta is a broadening, basically it is the broadening of the peak. So, if peaks are broadening, so that means higher the broadening, this crystal grain size will be lower. So, ordered region will be smaller. Okay. So, that is why in case of single crystal, as I told, peak will be very sharp, because this crystal size is ordered, that region is very large. So, L, that is the order, this length of the crystallite length L in single case, this L is very large. So, its broadening is inversely proportional to the size of the crystallites L. So, in case of single crystal, it is L is very large. So, broadening will be very small. So, that is why in case of single crystal, you get very sharp peak, and if it is polycrystalline, grain size will be smaller, that way L's become smaller, this broadening will be higher. So, that is why for polycrystalline sample, okay, for polycrystalline sample, this crystallite size are limited. So, that is why this peak, we get peak broadening. Measuring the peak broadening, one can estimate the crystallite size from this formula. Okay. And strain, you see strain means the in your sample if perfectly ordered, fine. Okay. It has a particular lattice constant. Now, if by some reason, whatever the reason, so if metal is strained, okay, If it is stained, then its dimension is different than the is a normal dimension, normal. So, lattice parameter will be slightly different than the normal one. So, that is what we tell this system is under strain. Okay. So, that means when system is under strain, then its lattice parameter is slightly changed. So, is d is affected. So, if d is affected, 2d sin theta equal to lambda. So, for the same lambda and d is slightly different, so theta will be slightly different. So, for unstained sample, unstained material, whatever the Bragg peak, position of the Bragg peak, Bragg angle, if it is stained, so this Bragg position, Bragg angle, it will be slightly, position will be changed. Okay. So, that is why here I have shown that red peak and this green peak. Okay. So, if red one is for unstained one, so the stained one will be this green one. Okay. So, from the shifting of the peak, one can basically study the strain of the system. Okay. So, I told, because these are very important these experimental tools to study the structure of the material. Okay. So, lot of things I told, and unfortunately I will not be able to show the data, or just because this I will show the machine, our XRD machine, and how we do the experiment, but only data I will not take from this system, because this system is slightly down now. Okay. So, in next class I will just demonstrate the experiment, mainly I will show the system. Thank you.